Welcome to this explainer. Today, we're going to explore the staggering, almost unbelievable breadth of a genius who literally bridges the gap between Isaac Newton and Albert Einstein. We're talking about the life and mind of James Clerk Maxwell. Now, it's a name you might know, but I guarantee it's a legacy you likely underestimate. We're going to see how one man's deep curiosity about the natural world unlocked the entire modern era of technology. Okay, let's just dive right in.
To really grasp the sheer magnitude of Maxwell's impact, well, we don't have to look any further than the words of Albert Einstein himself. Einstein definitely didn't mince words here. He said, "One scientific epoch ended and another began with James Clerk Maxwell." In fact, Einstein actually kept a framed photograph of Maxwell right there on his study wall. You see, Einstein's own revolutionary work on relativity and quantum theory relied entirely on the foundation that Maxwell built.
So the difference between these two eras is brilliantly captured right here. Before Maxwell, physics was pretty much entirely defined by Newton's mechanical world. Think of it like a universe of tangible objects, things physically bumping into each other, like billiard balls, with forces acting directly on matter. But after Maxwell, we enter Einstein's field theory world. This is a universe governed by continuous, invisible, abstract fields. Maxwell was the true visionary who realized that the fundamental building blocks of the universe aren't just solid objects, they're these intangible fields extending all throughout space. He basically provided the essential bridge between two completely different ways of understanding reality.
So, how exactly did he pull this off? Well, our roadmap today covers 4 distinct acts. Act 1, Saturn's rings and gases. Act 2, the first color photograph. Act 3, unifying electricity and light. And finally, Act 4, the poetry of physics.
All right, let's get into Section 1, Saturn's rings and gases. Long before he was decoding invisible forces, Maxwell actually started out with an astronomical mystery that had completely baffled scientists for 2 whole centuries. What on earth are the rings of Saturn actually made of? Back in 1856, Cambridge University hosted the Adams Prize to finally find the answer. The mathematics required for this were so overwhelmingly difficult that Maxwell's essay was literally the only entry submitted. He used pure math to prove that the rings could not possibly be a solid disk, and they couldn't be a liquid either. Instead, they had to be made of countless individual rotating particles, or, as he delightfully called them, flying brickbats. And honestly, the most amazing part of this? In 2004, nearly 150 years later, NASA's Cassini probe actually arrived at Saturn and proved his mathematical conclusion was absolutely spot on.
Having totally conquered the massive macroscopic scale of planetary rings, Maxwell then turned around and zoomed all the way into the microscopic scale of gases. He realized that gas molecules actually behave a lot like those countless particles swirling in Saturn's rings. But instead of trying to track every single tiny particle, which would be impossible, he introduced a groundbreaking concept. He used probability. He created the Maxwell distribution, which was a formula that calculated the varying speeds of different molecules in a gas. This was literally the very first time probability had been introduced into physics, and it laid the absolute foundation for what we now call statistical mechanics.
Moving right along to Section 2, the first color photograph.
So, from the invisible microscopic collisions of gases, Maxwell suddenly shifted his focus to something highly visual, super practical, and great for learning. He wanted to understand how the human eye actually perceives color. In 1861, during a lecture at the Royal Institution, he unveiled an absolutely incredible experiment. He took a brightly patterned Scottish tartan ribbon and photographed it 3 separate times, once through a red filter, once through a green filter, and once through a blue filter. This gave him 3 black and white magic lantern slides. But when he projected those 3 slides back onto a screen, passing the light through those exact same red, green, and blue filters, boom! The images superimposed to reconstruct the ribbon in full true color. He had just created the world's very first permanent color photograph.
Now, the absolutely crucial thing to take away here is that this wasn't just some neat 19th century parlor trick. The RGB, or red, green, blue principle that Maxwell demonstrated that day, it is the exact same foundation used in the digital camera on your smartphone, the television sitting in your living room, and the computer screen you are looking at right this very second. He practically invented the entire visual language of the digital age. Now for the big one, Section 3, unifying electricity and light.
This brings us to the absolute pinnacle of his career. If inventing color photography and solving the mystery of Saturn's rings weren't enough, Maxwell was about to rewrite the fundamental laws of the universe. Just look at this timeline. It shows his obsessive progression. He started by looking at the experimental work of Michael Faraday, who had noticed these mysterious lines of force around magnets. Well, Maxwell wanted to turn Faraday's brilliant physical intuition into rigorous, hardcore mathematics. So over the course of almost a decade, from 1856 to 1865, he tirelessly chipped away at this problem, determined to figure out exactly how electric currents and magnetic fields interact with one another out in empty space. To really wrap his head around these invisible forces, Maxwell imagined space not as this empty void, but as a giant churning machine. Look at this 1861 diagram. He visualized magnetic fields as rotating fluid vortices. You can see those hexagon shapes there. But to stop them from rubbing together and creating friction, he imagined tiny little idle wheels or ball bearings sitting between them, which represented electrical particles. It is a brain-meltingly complex mechanical analogy. He was literally imagining a universe completely filled with invisible, spinning gears.
But, you guys, here is where his genius truly shines. He knew the gears weren't real. They were just a mental scaffold to help him picture it. By 1865, he completely stripped away all these clunky mechanical models. He realized that he didn't need the physical wheels at all. The mathematical equations governing the invisible fields were completely sufficient on their own. He boldly declared that these continuous, invisible fields actually are the primary reality of the universe.
And the result of that massive realization? Maxwell's equations. These equations perfectly describe exactly how electric and magnetic fields are generated and how they interact. They showed that a changing electric field actually creates a magnetic field, and vice versa. Because they constantly trigger one another, Maxwell proved mathematically that they could actually break away from wires entirely and travel freely through empty space as self-sustaining electromagnetic waves.
But then came the true light bulb moment. When Maxwell actually sat down and calculated the speed at which these newly discovered electromagnetic waves would travel, the math sped out a very specific number, roughly 310 million meters per second. Maxwell was absolutely stunned. Why? Because this was exactly the known speed of light. In one single breathtaking realization, he concluded that light itself is simply an electromagnetic wave. Think about that. Electricity, magnetism, and light were no longer separate things. They were all part of the exact same unified force.
Sadly, Maxwell died in 1879 at the young age of just 48, long before anyone could build a machine to physically prove these invisible waves actually existed. But a decade later, the German physicist Heinrich Hertz built this brilliant apparatus. By creating electrical sparks on one side of a room, he was able to detect a current in a metal loop all the way on the other side. He had successfully generated and detected radio waves, conclusively proving that Maxwell's incredible equations were right all along.
Finally, let's wrap up with Section 4, the poetry of physics.
You see, behind all these mind-bending equations was a deeply human, fun-loving guy who was incredibly proud of his Scottish roots. This watercolor, actually painted by his cousin, shows a scene near his family home. If you look closely in the background there, you can see adults playing ice curling on the frozen loch, and Maxwell was right out there with them. He was a modest, grounded man who absolutely cherished his time with family in the Scottish countryside, far removed from the stuffy, serious academic halls of Cambridge.
He also had this wonderfully quirky sense of humor, which he loved to express through poetry. For instance, he took the famous romantic Robert Burns poem Comin' Through the Rye and completely rewrote it. He turned it into a hilarious parody all about Isaac Newton's laws of dynamic impact and bodies colliding in midair.
And his colleagues just loved this nerdy side of him. He even used to publish some of his lighter poems in a prestigious scientific journal, Nature. But he wouldn't use his real name. No, he signed them simply as dp/dt. To anyone else, that's just a standard thermodynamic equation. But if you actually solve that equation, the mathematical result is JCM, his initials. Just a brilliant, funny little mathematical inside joke.
But it's important to know his poetry wasn't just for jokes. Maxwell held a very deep Christian faith, and this faith fundamentally informed his scientific discovery. He deeply believed in the fundamental unity of nature, which is exactly what drove his relentless quest to unify electricity and light. This faith also fueled his immense capacity for love, especially for his wife Catherine, who actually worked alongside him and assisted with his experiments. In a beautiful poem dedicated to her, he wrote these words, reflecting that while the mind and will may eventually fade to dust, love endures, even beyond death. It just perfectly captures a man who saw absolutely no divide between the mechanics of the universe and the poetry of the human soul.
Which leaves us with this final thought for today.
Just think about your day so far. The Wi-Fi you use, the Bluetooth connecting your headphones, the GPS in your car, even the microwave in your kitchen. Where would our modern world be without the man who first envisioned the electromagnetic field? James Clerk Maxwell laid down the invisible tracks that the entire 20th and 21st centuries run on. So, the next time you send a text or snap a color photo, take a quick moment to appreciate the Scottish poet-physicist who made all of it possible. I highly encourage you to go read more about this incredibly unsung hero. Thanks for joining me on this explainer, and keep exploring.